Okay, hello everybody. Let's go through a quick review of everything we've talked about in the entire universe except the first few chapters, and let's focus on the last 6 chapters: Galaxies, Cosmology, and Life in the Universe. So we're going to cover chapters 25, 26, 27, 28, 29, and 30, but those first 4 are pretty much all about galaxies. So let's have a quick review. A galaxy is a disk of stars, like a pizza of stars, and sometimes it looks dark through the middle, but if you look at it through radio waves, you can see that it's very light. So what's happening, so rather than gamma, X-ray, UV, visible, infrared, and radio, if you just look at visible light, or the light that your eyes would see, that's what you see. If you look at the same picture in radio waves, you can see that there are stars there emitting radio waves, but the clouds and gas are absorbing these other frequencies of light, which we call interstellar reddening, because the light, all the blue light gets deleted and only the red, or at least on the red end of the spectrum, remains. So this is the blue side, this is the red side of the spectrum. Ultraviolet is blue, like a black light, everything's glowing purple. Radio waves are on red or infrared side. If you look at it from the top down instead of through the disk, then you'll see a bar structure with a spiral coming off of it. So this is a barred spiral galaxy. Our galaxy, the Milky Way, is like this. The sun is about halfway out from the center, and in what's called the Orion Spur. The disk itself is not the whole galaxy. There's also this large halo around it's a spherical halo. So you've got a disk in the middle plus a sphere with globular clusters. And all these things are globular clusters. And if you zoom in on a globular cluster, it's just a giant collection of stars. But what do you notice? No gas, no dust. So that means no new stars forming. And if on a typical HR diagram, you would find stars on a line. But the bluest, hottest stars, which are on the top left of this HR diagram, they die quickly. So when you look at an HR diagram for a globular cluster, what you see is this. You see stars like that. So no stars that are blue still there. So that means these globular clusters haven't had new stars forming for a very long time. And you can see that all of the stars from here on have died. These globular clusters have been around long enough for that to happen. So a star like the sun, which is at 1 solar mass and about 5,700 Kelvin, has a lifetime of about 15 billion years. So the stars here are just dying in this globular cluster are between 10 and 15 billion years. So we think the universe is about 13.7 billion years old. The globular clusters all have stars that are about 13 billion years old. So that tells us that they're some of the oldest objects in the universe. Galaxies have 3 different sort of shapes: a spiral shape, a elliptical shape, and a irregular shape. Now, a spiral galaxy, look at it, pretty colors, lots of gas, lots of dust. An elliptical galaxy could be very, round, circular to very football shaped. The eccentricity of the ellipse. No gas, no dust, no new stars, gold color. That's the classic sign of an elliptical galaxy. A regular galaxy could be merging, could be a lot of different things going on there. You can classify galaxies by their shape. An elliptical galaxy could be very elliptical or spherical and or very elliptical. So as the galaxy gets more and more football shaped, it gets a larger number after the E for its classification. This is called Hubble's tuning fork because it looks like a tuning fork, but how often have we seen tuning forks used for like tuning a piano? You use a piece of metal, you go bong, and it sings a pitch. So there's no reason to do this, but this is how Hubble classified galaxies. They're spiral or barred spiral or ellipticals, and then you get your irregulars. Every galaxy has a supermassive black hole at the center. This is the one at the center of our galaxy. There is something right here in the middle, right there. All these stars are orbiting, but what it is, we can't see. But if you look, because of Kepler's laws, you can calculate this orbit, you calculate how long it takes, you can calculate the mass of that thing, because that mass is what causes the gravity. So if you measure the gravity by looking at the orbit, you can infer the mass of the supermassive black hole. It is very massive to get the stars to do this, which when we look at all galaxies, we see this repeated over and over again. And it was an open question until recently whether supermassive black holes are common, and they are. When they are active, called an AGN or an active galactic nuclei, when the nucleus of a galaxy is active, it shoots these gamma rays into space. We call them gamma ray bursts or just gamma ray emissions if we don't see them directly. But if you look right down that thing, you're gonna get gamma rayed and it's gonna not feel very good. But that's what you see in a supermassive black hole. Can accelerate the material that's orbiting it to a very high temperature, and then that with the magnetic field shoots stuff out into space. So that's another property of galaxies, is they have a supermassive black hole. Another property is they have what's called dark matter. And our idea of dark matter filling the halo of a galaxy comes from Kepler's law, which predicts that the further away you are, so the further you are away from the center of a mass of objects rotating under gravity, the slower you'll orbit. So the orbital speed goes down the further away you get. Like in our solar system, you would expect as you get further from the center of our galaxy that the stars would slow down as well. So a normal orbiting situation, look at Neptune way out to the right, going so slow. But in our galaxy, when we look at the stars, they're not doing that way out there. It's as if they're, this is exaggerated, but it's like that. So no dark matter over here, and this is the galaxy. So no dark matter over here, and this is the galaxy that we with dark matter over here. So no dark matter. Look at this little guy, just barely trucking along. Whereas if we look at this guy, oh my gosh, he's just flying around here on the edge. Okay, so that's what we observe. We observe this, but we don't see enough gravity to cause that. So the way you get gravity is to add material, add mass. Mass causes gravity. So dark matter is just, let's just assume there's more material out there than we can see, and that's causing the gravitational effects we're seeing. Simple enough. We see that with every galaxy so far. So these are all galaxies here, and these are their rotation curves, or the orbits of the stars. As you go from the center, they don't fall off like you'd expect. They don't fall. They don't get slower when you get further away from the center of the galaxy. More evidence for dark matter. So that's our galaxy thing. Now, dark matter. We require dark matter to form the universe that we see. This is a video from two simulations, one where there is no dark matter and one where there is dark matter, and the dark matter universe matches what we see. This, without dark matter, we get a different universe than we expect. So that's more evidence. Another set of evidences is this two galaxy clusters merged and passed through each other, and when that happened, the dark matter and the stars and stuff kind of just went on through because they didn't interact. But the hot gas that makes up the majority of the mass of this cluster, they crash into each other and interact electromagnetically, so they slow down and they separate. So in this galaxy, the hot gas separated from the other things, and when we look at the net result, we see it looks like most of the gravity is there and most of the gravity is here, even though from what we can see with our eyes, most of the mass is here. And again, we know that mass causes gravity, so the fact that we see most of the effects of gravity coming from this region and that region, the blue here indicates the highest gravitational influence. And so those blue regions are where gravity is the strongest, whereas the red regions indicate where there's the most amount of material. So again, that indicates that there's something there that we can't see. So it's some of the best evidence. And this is just an animation of the bullet clusters. So two galaxy clusters merging, and then you can see the dark matter, the blue color, separating, but the red stuff, the hot gas, slowing down and also separating. So that's the evidence so far for dark matter. There's some other things, but that's pretty much covers the gamut. So what could dark matter be? It could be weakly interacting massive particles. It could be called WIMPs. Could be machos, massive compact halo objects. So it's either a new particle like an axion that we haven't observed yet, or it's an object that we know and we just are undercounting it. So black holes, for example. So I think it's quite possible that it's a combination of both, of a new particle of some kind that we need to discover, but also we're not counting all the black holes that are out there. So intermediate mass black holes or small mass black holes could definitely make up a bulk of the dark matter problem, as well as something like an axion. There's no SUSY, neutrinos probably not. Probably not dark Jupiters, probably not solitons. So probably a combination of black holes and axions, but what do I know? Who knows? We'll see. Galaxies form from the bottom up. So in a normal solar system, you have a ball of gas, and that collapses down under gravity to form the stars and the planets at the same time. The question with galaxies was, is that the case with galaxies? Is there a large thing that collapses down, hydrogen gas collapses down, forms the stars and the whole galaxy all at once? Looks like no. Looks like starts with small things that collide and stick together and build up to bigger and bigger and bigger and bigger objects. So the prediction of that is when we look deep into space, like this picture, and we look at galaxies, we should expect to see that the galaxies get smaller the further we look into space, because we're actually looking back in time. So as the universe gets younger, the galaxies should get smaller, because as time goes on, the galaxies would merge into bigger. And that is exactly what we see. When we look at all those galaxies in that picture I just showed you, they're all moving away from us. And so Hubble measured this after he discovered that Andromeda was a whole galaxy, and then started looking at all these other galaxies and like, these are all galaxies, and then measuring their recession velocity by their redshift. He noticed that the further away you were, the faster you were moving away from us. So what does that mean? It means if you're a galaxy here today and you're moving away from us, because you're moving 15,000 kilometers per second away from us, if we wait, over time, you're going to move further away. But when you move further away, you don't just move further away, you move further away at a faster and faster rate, because as you're going to the right, you're gaining speed. So what does that mean? It means as these galaxies move away from us, they actually move away from us faster and faster and faster as they go. So that means that the universe is expanding. That's what that means. And it's true for every galaxy we measure. Every galaxy we measure in every direction, they're all moving away from us, except for the local ones near us where we are gravitationally bound. For example, Andromeda and the Milky Way will collide one day form a super galaxy, but beyond our gravitational reach, the universe is expanding. So Hubble said, if that's the case, then the time it would take this galaxy to reach this point, we just rewind the time back, and we can get an estimate for the age of the universe. And that gives us about 13.7 billion years, 14 billion years, just from this measurement alone. And so that implies that there was a time in the history of the universe when everything was much closer together. And if that's the case, when things get closer together like that, the temperature goes up. So we predicted that if we look back in time, we see galaxies getting smaller and smaller, getting closer and closer together until they're right on top of each other. And it's so hot that the whole universe, there's no stars, there's no galaxies, there's no nothing. It's just a soup of particles. It's just energy. It's just pure energy and atoms cooling down. And then from there, you're going to get stars and stuff. And that we can actually see that part of the universe from about 400,000 years ago. 400,000 years after the Big Bang. That's when that's when electrons got trapped around the protons to form hydrogen. And when that happened, when the electrons recombined, so we call it the era of recombination, when that happened, light could travel without scattering off electrons, which means light could travel long distances, and you could actually see something because the light could reach you. So the fog lifted in the universe cooled down enough. So when we look out into space, deep, we look back into time, we can actually see that time of the universe when it was a single temperature. And that was discovered in 1964. Something like that. They observed the cosmic background radiation. And then if we want to probe this time before, back to the beginning, we have to use a particle accelerator to smash the particles together to do that, to create those temperatures. So if you imagine taking the whole sky and unwrapping it into this map here, Kobe, then WMAP, then Planck, or Planck, looked at the temperature of the cosmic background radiation, and this looks like they're a very red and a very blue, so must be very different temperatures. This is all very close to the same temperature, very slight temperature fluctuations. So what this picture shows you is that the soup of the universe was basically the same temperature everywhere you look. And This is another, if you look out into space, you see our galaxies, you see, keep going deeper back into time, you see the cosmic background radiation, and then from there, there's this little gap that we can't see all the way to the beginning, but we can do some physics to try to calculate what it would have been like in order to create the cosmic background radiation that we see, and therefore the universe that we see. And then we have this video here. So this is the observable universe. If we are at the center of it, you can see the map of the galaxies with the Sloan Digital Sky Survey in the middle. You see a couple of cones missing, which is where our galactic disk blocks our view. So you can see basically here are where all the galaxies are at. And then there's this big gap until we get to the cosmic background radiation. So there's two problems with the Big Bang Theory. It wasn't widely accepted until the 60s and 70s, and now it's pretty well accepted. It explains a lot of the observations of the universe, but there's two big problems with it, two predictions that it can't explain, or two observations that it can't explain. One of them is that when you look out into space, we see that the cosmic background radiation from here or here is the same temperature. And one of the laws of thermodynamics says that happens when two objects are in contact long enough, they will reach the same temperature. But these are on opposite sides of the universe. There's no way that they were in contact. So how could they possibly be the same temperature? You would expect a hotter region here and a colder region here, and not this tiny speckled differences that I showed you in the WMB or WMAP or Planck maps, but significant differences. So that's called the horizon problem. How does this part of the universe see over the horizon, see that part of the universe? And by see, we mean be in contact long enough to actually reach the same temperature. The second is called the flatness problem. So if this is me today and into the future, that's my world line. As I travel into the future, I will just keep going into a new, future all the time. If the universe has enough material in it, because we know around a star like the sun, we know that space gets warped. That's what causes gravity. So we know that space and time can be warped. The question is the universe between the stars, is it really warped? And so if the universe had if there was enough material to cause a warping of the universe like this, so that if we were at this and we go through forward in time, keep going in time, going around to the other side of the globe, and then back, there would be a time in our futures where we come back to where we are today. That's one of the predictions if the universe is warped overall. Another one, it could be warped like this. So you just keep going forever, the same thing, but it would be sort of this expanding, accelerating universe. Your future would go faster and faster. Our universe is flat, observations show. So that means our critical density is exactly the amount of material in our galaxy. The amount of material in our universe is exactly balanced by the forces of energy and expansion that are causing the universe to expand. So the force of gravity in from all the stuff is exactly balanced with the force of the expansion going out. That seems too good to be true, because it could be any value. Why are they linked like that? Maybe we'll find out that it has to be flat. It has to be a critical density of 1. Maybe that's what we find out. But right now it seems like it could be any number. It could be 0.1, could be 0.42, could be, whatever it is. Could be 42. The question is, why is it exactly 1? And BICEP 2 is an experiment trying to look for evidence of the hypothesis that would explain this. And the hypothesis is called the theory of inflation, or the inflation hypothesis. And it's in Antarctica, and it's looking for microwaves. It's looking for the cosmic background radiation, looks for a certain polarization of it, it leaves an imprint of inflation. So what's the idea behind this? It's that if the universe, when it first formed, you would expect it to be kind of lumpy. This is hotter, this is colder. The universe would have some localized, lumps in it. And then the temperatures would be slightly hotter here, slightly colder there. The lumps would be, so it wouldn't be the same temperature, and it wouldn't be perfectly flat. It would be pretty lumpy. So one idea is that, maybe right after the universe formed, there was just this huge push that just, wow, and just imagine forcing the universe to expand fast enough that it couldn't expand any faster. It filled up the whatever space it could expand into, in the sense, and the force of that just flattened out the universe into a nice ball, and the temperature were all the same at that point because the universe was small enough that it was the same temperature, and it just created this, thing. So the idea is inflation that explains that. The it's an outlandish idea that the universe expanded, an absurdly quick, and there's no mechanism for inflation. There's no why did it do that or how. It's just that if it did it, it explains the universe. So if we observe inflation, then the next step would be explaining how inflation happens or what the mechanism behind that. So if inflation is not the thing, the Big Bang Theory has problems. And so stay tuned for that. Our universe is expanding. The light from distant objects, like this star, the light left, and if we're right here in the middle, the light hasn't gotten to us yet. But if we wait a little bit longer, this black line moves out, and that light will start to reach us until the black line, and now the light has reached us. So what this is showing us is that we have something called an observable universe, which is as far as we can see, because the light takes time to reach us. So the universe can still be infinite. We just don't have access to all of it yet. So our observable universe is finite, but our the universe itself, there obviously are objects out there that we're waiting for light to reach us. Now, the interesting thing is that I just threw my pencil. The interesting thing is that the universe is also expanding. So it turns out that these stars actually, the light is coming towards us, but the universe is expanding so fast that the light is never going to reach us, actually. So some of the objects that are out there we'll never be able to see, even if we wait for a long time. And since the galaxies are moving away from us, and since their velocity is increasing every time they move away from us because of the expansion of the universe, eventually we will not be able to see any galaxies because they will be moving faster away from us than the light they are emitting could reach us in a given amount of time. So the galaxies are slowly going to get redshifted until microwaves and then eventually disappear. So we are in a nice place in our universe in the history of it to be able to study it. So we should. Now, this leads to an interesting idea, because if there is a universe beyond our universe, then someone is there, whether it's a star or an alien civilization. So imagine people at the centers of these observable universes. If the universe is continuing to expand like this, these universes will never be able to be in contact. And so, these are people as far as we care, are in different universes, even though they are in the same universe, because they could never communicate with each other. They could never be a part of each other because the expansion prevents any sort of interaction here. And you could imagine statistically, if you play cards enough time, you're going to get the same hand again. The same thing is true in a universe that is infinite. If the universe is infinite, then eventually it will repeat itself. So there must be another universe where I'm in it and is doing other things. So that's called the multiverse idea, or parallel universes. There's also the many worlds. So many worlds. And if you want to know about this, look up Sean Carroll. He's got a lot of stuff on that. He's a big proponent of it. Many worlds hypothesis says that a fundamental particle, when it actually makes a decision, if you want to calculate the possible future of a particle, you actually have to consider all the possible futures that it could take, all the different paths, all the different possible states it could be in. And you cannot predict which one it's going to be. That's the thing about quantum mechanics. You can only calculate a probability and measure the result of you can't know what the event will be. You can only measure it and have a probability distribution for it. So Sean Carroll says, well, that actually what that means is that there is a universe where every possible outcome happens. So every time you make a choice, every time the particles in your body make a choice, a new universe is being split off, and it's parallel with us right now, and da 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 da. And there's, mathematically you can do this. I think he's nuts, but what do I know? So he sells a lot of books. Maybe I should write a book about that. Um, okay, so now let's talk about life in the universe really quick. So we got the chicken and the egg. We got life on Earth. What do you need for life on Earth? You need these four molecules. So if you've seen the movie Gattaca, 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 that's our DNA. When you look up the sequence of your DNA, you're going to see Gattaca. That's the programming language. So how does life work? You split this DNA off and you get an RNA, which is half of your DNA, and then the RNA has these little spots where you can stick stuff to, and so basically that thing goes into a ribosome, or the Golgi apparatus, and goes in there, and then where these little ends are, you can get proteins, amino acids to stick to it, and then the amino acids are used to build a protein. And so this is basically the instructions for building all the things, cell wall, all the stuff in your body for all the things you need to do. So in order to make DNA like this, you need these molecules. So you need the nucleotides, you need amino acids, and you need sugars, and all of those molecules go together to make up the cells and do the functions in our body that our bodies use. And it turns out that these nucleotides, amino acids, and sugars, and those sorts of things are abundant in the universe. They're everywhere. We can see them. They're obviously everywhere on Earth, but they're in nebula, they're in the clouds of Jupiter and stuff like that. These are natural things, which makes sense. We are part of nature. We should be made of these things. And then your DNA is made of those things, which make up this. That's your chromosome, which is just tons of DNA wrapped up. And then that chromosome goes into your cell, and then parts of your chromosome are red, and whichever part is red determines the cell that it's in. So that's why your skin cell has the same DNA as a retinal cell, but different part of your DNA is red in those different cells, so it functions differently. And as you get older, those start to function incorrectly, and so you have cells behaving as something that they're not, and hair growing out of weird stuff. So anyway, the point is that this stuff is natural. It's around all the time. So how can you generate some of these? There was an experiment in the 50s. Obviously, there's been more since then. But these experiments show that, it's pretty easy to produce the molecules that we need in order to make life. Now, this doesn't mean that this is how you get life, or that if you have this, that's sufficient for life to develop. But this was just an example of, and then obviously since then we've seen it over and over again, that life, the building blocks of life, are naturally occurring, and so the question is that enough to make life? Even the DNA structure, the helical structure, that's a common, thing in the universe to see. So it's not that anything about life is unusual. The unusual thing is that we're here, I guess, because we can't see that anywhere else in any other planets in our solar system, but no other solar systems around. So life on Earth evolved from a single object. So you can think of this picture, what it's saying is that everything that has 2 eyes, 2 ears, a nose, all came from, a common ancestor. That the first one to have 2 eyes, and it worked really well, and that was copied and pasted. The way I think about this is like every phone today, every smartphone today, looks like the very first iPhone. Once Apple released the iPhone and it worked so well, that platform, the touch screen, the camera, the speaker, that was it. Every phone since then, for the last, what is it? It's almost 20 years now, has been that model. So it's like, boom, right here, whatever that happened, it's like that was the winning, platform, and then all these different versions. The apes are the androids, and the apples are the humans, or whatever, and the Nokias are some pig or something, and all the different animals. So they all have the same sort of look: 2 eyes, 2 ears, 2 nose, a mouth, 4 things that you either walk or grab stuff with. And then you keep going back, and then you see that all of these things from like here and on all have mitochondria or something. I don't know if protozoans do or where the mitochondria enters in here. I should look that up. But at some point, mitochondria gets into a cell, and I really don't know how early that happened. I should look that up. But the idea is that when that happened, that opened doors for a new thing. And so this is called evolution, natural selection, where we can see that the things that made life robust were replicated and copied and pasted. And if when it was replicated, if they got rid of it and it didn't work, then that thing died. Okay, and the best example of this is the color of our skin. On Earth, let me draw Earth like this. The sunlight, let's say it's direct sunlight right onto the equator pretty much. But at the northern latitudes, the sunlight is not as intense. So when you're on the equator, what you notice is that people have a lot darker skin. When you go up towards the North Pole or the South Pole, people have lighter skin. The question is, there's nobody at the South Pole, I don't know why I drew that, but if northern England or whatever, very light skin. Why? Because you need vitamin D, you need nitric oxide, you need infrared radiation into your mitochondria. You need all these things that come from the sun to survive and thrive. And if you don't have those, you get diseases and you die. Okay, so in Africa, if you go outside, you're going to get pulverized by ultraviolet radiation because it's so intense, and you'll die because you get skin cancer. So, natural selection selected for, in the northern parts of the world, all these people who had dark skin died because they didn't get enough vitamin D, and so people started to get lighter colored. At the equator, if you had lighter skin, you died of skin cancer before you had a chance to procreate, so people started to get darker skins. So, you could go outside for longer. You could hunt for longer because you were in the sun for longer and you weren't getting burned or tired or whatever. So, that's an example of natural selection, how it depending on the environment you are in, you adapt to it. So the quicker you adapt, the better fit you are to the environment. You don't have to actually be fit to be survival of the fittest. That means you fit in the most in the situation. So if you can adapt, if you can fit in, you are more likely to survive, you are more likely to thrive, and therefore reproduce, and your traits will be passed on. And if you don't have those same features, then you won't reproduce, your traits will not be passed on. And so that's how natural selection sort of chooses the most fit for the environment that it's in. Okay, so the question, that's all life on Earth. The question is, why is it on Earth? And Earth is in what's called the habitable zone around the sun. So it's not too hot, not too cold, just right. The sun sits around for a really long time, putting out the same amount of heat. It makes a really nice, you don't want the environment you are in, trying to evolve life in, to be changing all the time. That's the concern with climate change, is that we change the climate faster than the living things that are on Earth right now can adapt to them. And, you could have a mass extinction event, which would collapse ecosystems and therefore our farming, and then our food would run out and blah, blah, blah. So we're worried about climate change because of how quickly our environment could change, which will make it hard to adapt to. Okay, other things in our solar system, Europa and Enceladus, they've got liquid water oceans. Theoretically, all of the ingredients necessary for life. They are outside the habitable zone, but they're close enough to Jupiter and Saturn to get tidal energy and heat and have those liquid water oceans. So they might be warm enough for life, might have been stable enough for a long enough time. So we're interested to see if life evolved in those places. Mars dried out pretty quickly, but it had water at some point in its history, and it only took 100 million years for life to evolve on Earth, even in the most primitive forms. So we're really curious to see if even the most primitive forms of life came to be on Mars, and if there's any evidence of some very early biological life. No idea. It'll be really hard to find, but it's possible. In our Milky Way, most of the stars are small red stars, which means they live for a really long time and they're very stable. So that's one of the things we think is necessary to develop life. I mean, it took 4.5 billion years for humans to show up on Earth. So we needed an environment that was stable relatively for 4.5 billion years. Of course, we needed the dinosaurs to get out of the way. So thankfully, a meteor came and wiped them out. But that's another example that maybe if that hadn't happened, dinosaurs would still be roaming around on Earth, which is kind of crazy to think about. So the question then is there life everywhere or is it very rare? So these white things represent stars that have life on them. And then on the bottom, maybe we're the only one. And that is called the Fermi paradox, which is if life only took 100 million years to evolve on Earth, and there was nothing special about Earth in the sense of the raw ingredients were there, they're there everywhere. You know, the sun is a star. There's other stars out there. The question is, where's all the aliens at? And that's the Fermi paradox. If it's so easy, why don't we find life everywhere in our solar system, everywhere in the universe, in our galaxy? So there's several possible solutions to that. One of them is the dark forest, which is aliens are there, they're out there, they see us, and they don't want to tell us. So they're hiding behind the trees. We are in the dark forest, and nobody wants to let anybody else know that they're there. It could be that we are one of the first. It could be that we are the only ones. That's definitely possible. But that doesn't really answer the paradox, because the paradox is, why would we be the only ones if it's so easy for life to develop? I think my camera just overheated. It's getting too hot because I'm too hot. Cool off. And then there's this idea of the great filter. And the great filter is this idea that, something is going to kill us. Either we are ahead of it or we are still behind it. And so that means it's ahead of us or we are behind it, which means it is ahead of us. So that could be nuclear war. You know, if Putin launches a few nukes and we retaliate with nukes, suddenly there's a ash high in the atmosphere that doesn't go away for 100 years and, doesn't let sunlight reach the earth and kills all the life. Okay, and then life dies. And then we don't make it into spacefaring civilization and we're trapped on the planet forever. Who knows? So that's one. That's a great filter. Another one would be climate change. Let's say we create a overwhelming greenhouse effect like Venus, and the surface just becomes 200 degrees in the next 100 years, and you just can't live on the surface. And well, what are you gonna do? You can't launch a rocket. It's gonna be too hot. All these problems. So that's another one. Maybe a meteor's coming or a comet's gonna hit us in the next couple years, or the next 100 years or something, before we really get a base in space to launch. Maybe space is too dangerous. Maybe no life can exist between the stars off of a planet. Maybe that's just not possible yet. Maybe it's so hard that it takes a long time for life to get to that point. So maybe nobody's gotten there in our universe. So these are examples of great filters. So that's the Fermi paradox. That's life in the universe. And that's the end of my review. I hope you learned something. I hope you knew all this stuff already because you paid attention in class. But if you didn't, let me know if you have questions. And keep thinking. Appreciate where you are in the universe. And I will see you later.